All right, here is part two. Go back to our whiteboard. All right. Question 15. A balloon absorbs 35 gram or joules of heat. So because it absorbs the heat, that should have a positive sign. That's going to be our Q term. And then it expands and it does work. So that means it's doing work on the surroundings. So it would be losing energy as work. And delta E, or the change in energy, is equal to Q plus W. So in this instance, we would have a positive 35 joules plus a negative 15 joules. So we should end with a positive 20 joules for our delta E for the balloon. An unknown metal has a mass of 50 grams. So we're going to use Q equals mass times that specific heat times the change in temperature, or Q equals MCAT. We have the metal, we don't know its identity, but we do know its mass. We know that it absorbed 800 there we go, joules of energy. And we know the temperature increased from 42 or from 25 to 42.7. So that's our final temperature. That's our initial temperature. So then our delta T should be 17.7. So we're going to have 800 joules is equal to 50 grams times our specific heat, which we don't know because we don't know the identity of the metal. And then 17.7 degrees C. So if I divide both sides by that, I'll get joules per gram degrees Celsius, which are the units for specific heat. And we get C sub S equal to 0.903 joules per gram degrees Celsius. And when we go to our last page there with all the different specific heats for different metals and substances, we see that that 0.903 matches the specific heat for aluminum. Now we have 2 grams for question 18. 2 grams of naphthalene and molar mass 128.164. It's burned in a bomb calorimeter, and the temperature increases from 24 degrees to 30 degrees. So we have a delta T of 6 degrees Celsius, and our heat capacity for our bomb calorimeter is 5 kilojoules per degree Celsius. So I can take our specific or our heat capacity for our bomb calorimeter, multiply that by the change in temperature when it combusted and absorbed all that energy, and we can see that combusting 2 grams of naphthalene should give us 30 kilojoules of energy. And we want to know how many kilojoules for a mole. So we need to find out then from that 2 grams, how many moles of naphthalene is that? So we would divide by the molar mass. and that is 0.0156 moles. So if I put my 30 kilojoules over that, what I get is 1,922 kilojoules. Question 19, we've got a 40-gram gold nugget. We know the specific heat for gold is 0.129. Or no, sorry, not gold, a nugget of silver, sorry. There we go. So this is silver, and the specific heat for silver is 0.235 joules per gram degree Celsius. Initial temperature is 70 degrees Celsius. And then we have 65 grams of water. And it starts at 28 degrees C. And I want to know what's the final temperature of the silver, and also what would by default be the final temperature of the water. So this means the silver starts at a higher temperature, so it's going to lose thermal energy to the water, and its temperature is going to go down, and the water's temperature is going to go up. That is going to happen until they reach equilibrium, and they will end at the same final temperature. So we have negative Q system equals Q surroundings. However much energy the system loses, the surroundings would have to gain that. So I'm going to have a negative in front of my Q MCAT here for silver. We don't know the final temperature, but we do know the initial temperature. And that's going to be equal to positive mass of the water times its specific heat times its final temperature, which we don't know, but which is the same final temperature as the silver. So we only have, again, one variable. 40 times 0.235 gives me negative 9.4 TF plus 658 equals 271.96 TF minus 7,614.8. So I want to isolate T sub F. I can do that by adding the 7,614.88 to both sides. And adding 9.4 TF to each side. When I do that, I get this, and then to isolate T sub F, divide both sides by that. and we get 29 point, there, 4 degrees C as our final temperature. Which of the following is an example of an endothermic process? Remember, endothermic absorbs energy. So it's going to have a positive Q term. And out of all of these, the only one that takes energy or heat to make the thing happen is ice melting. As we go from a solid, which is very rigid and the molecules are very close to each other, we need to add energy into that to get it to become a liquid. So it's going to absorb that energy from its surroundings, and its surroundings are going to get colder. Whereas in all the other examples, they're actually going to release energy into their surroundings for the process to happen, and that would actually make the surroundings grow warmer. And then lastly, we have an alloy that is 65% copper and 33% zinc and 2% tin. So what we have here is a mixture, or one could call it a solution, and we want to know what would be the solvent. And the solvent is always the majority component. So that would be the copper in this instance, and these would be our solutes. So that's everything. Hopefully this was helpful. Skip around if you need to, watch it at a faster speed. If you have any questions afterwards, feel free to ask. If you think something was wrong about your Scantron, feel free to stop by office hours. We can pull that Scantron and check it and make sure it's accurate. Otherwise, I will see you all Monday.